In this video we're going to look at the calculus of some of the polar curves that we investigated in the previous video. So if we've got the curve r equals f of theta, then dr by d theta gives us the rate of change of r as theta changes. And if we need to find the maximum and minimum values of r, then they may be obvious from the function f. If not, they can be determined by solving the equation dr by d theta equals 0. To find the equation of the tangent or normal to the point of a curve on the curve, we're going to need the value of dy by dx at that particular point. That's not too badly done because we know that x is equal to r cos theta, which is f of theta times cos theta. And we know that y is r sin theta, which is f of theta times sin theta. So in other words, we have x and y given parametrically in terms of the parameter theta. So if we wish to find dy by dx, then we can say that dy by dx is dy by d theta divided by dx by d theta. So let's start with an example. Polar curve C has equation r equals 2 plus cos theta plus sine squared theta. Is shown in the diagram. We've got to prove that the smallest circle with centre the pole that totally contains the curve C has an area of 169 pi divided by 16. Well, to find this smallest circle that totally contains C, we need to find what the maximum value of r is. Now we've got r is 2 plus cos theta plus sine squared theta. It certainly isn't obvious in this case what the maximum value of r we can obtain is. So, given the value of r, we can straight away say that dr by d theta is minus 2 sine theta plus 2 sine theta cos theta. And for the maximum or minimum value of r, we know that dr by d theta is going to equal 0. So putting dr by d theta equals 0, we've got minus sine theta plus 2 sine theta cos theta must equal 0. In other words, sine theta times by 2 cos theta minus 1 must equal 0. Which tells me that sine theta is 0 or cos theta is a half. Which in turn gives me the fact that theta can be 0, pi, pi by 3, or 5 pi by 3. The corresponding values of r are 3, 1, 13 over 4, and 13 over 4. So the maximum possible value of r is 13 over 4. So the smallest circle with centre the pole that contains C is going to have a radius of 13 over 4, so it's got an area of pi times 13 over 4 squared, which is 169 pi over 16. And we can see in this diagram the original curve that we had in red, and then the dotted circle has a radius of 13 over 4, so that's 3.25, and we can see that it just contains the curve C. For our second example, we have the curve C with equation r equals e to the 0.1 theta. For values of theta between 0 and 2 pi is shown in the diagram. We've got to find the polar coordinates of the points on the curve C where the tangent is parallel to the initial line. Now, if the tangent is parallel to the initial line, that means the tangent is parallel, if you like, to our x-axis. And anything that's parallel to the x-axis has got a gradient of 0, which means that we want dy by dx to equal 0. But we know that dy by dx is dy by d theta divided by dx by d theta. So we need dy by d theta to be equal to 0. Now y is r sine theta. So that in this case is e to the 0.1 theta sine theta. So the product rule is going to give us dy by d theta is 0.1 e to the 0.1 theta sine theta plus e to the 0.1 theta cos theta, which is the same thing as e to the 0.1 theta times 0.1 sine theta plus cos theta. And we want that to equal 0. If e to the 0.1 theta times by 0.1 sine theta plus cos theta equals 0, e to the 0.1 theta cannot be equal to 0. So we must have the 0.1 sine theta plus cos theta equals 0. And that tells me that tan theta must be equal to minus 10. In other words, that theta must be either 1.67 or 4.81 radians. In which case, the corresponding values of r is, when theta is 1.67, r is 1.182. And when theta is 4.812, the value of r is 1.618. Now for part B of this example, we want to find the polar coordinates of the point on the curve C, where the tangent is perpendicular to the initial line. Now, if it's perpendicular to the initial line, that means that it must be parallel to the y-axis, and the y-axis is a line with infinite gradient. So in other words, we're looking for points on the curve where the gradient of the curve is infinite, which means that we want dy by dx to be infinite. In other words, we want dy by d theta divided by dx by d theta to be infinite. In other words, we need dx by d theta to equal 0. We know that x is r cos theta, so that's e to the 0.1 theta times cos theta. So dx by d theta is going to be 0.1 e to the 0.1 theta cos theta minus e to the 0.1 theta times by sine theta. In other words, e to the 0.1 theta times by 0.1 cos theta minus sine theta. We want dx by d theta to equal 0. So that means that we've got 0.1 cos theta minus sine theta must equal 0. In other words, tan theta must be 0.1. And tan theta is going to be 0.1 when theta is 0.1 radians approximately, or 3.24 radians. If we have theta equals 0.0996, then the value of r is 1.01. And if we have theta is 3.24, then the value of r is 1.38. So we've got the 2 points there in polar form where the curve is, where the tangent is perpendicular to the initial line. Now, in the previous video, we made the comment that if we know that r is 0 when theta equals alpha, then the line theta equals alpha must be a tangent to the curve. But we never proved that proposition. But now we know how to differentiate our curves, then we can actually prove this proposition reasonably easily. Right, so we know that if we've got r equals f of theta, and we're using polar coordinates, and we know that x is r cos theta, y is r sin theta. So in other words, we've got x is f of theta cos theta, y is f of theta sin theta. And therefore, we've got dy by dx is dy by d theta divided by dx by d theta. And using the product rule, we can say that dy by d theta is f dash theta times sine theta plus f of theta times cos theta, and dx by d theta is going to be f dash cos theta minus f of theta sine theta. Now, when theta equals alpha, we know that r is 0. In other words, we know that f of alpha is 0. So the expression for dy by dx, or the gradient, simplifies to simply f dash alpha times sine alpha plus nothing over f dash alpha cos alpha minus nothing. In other words, f dash alpha sine alpha divided by f dash alpha cos alpha, which is simply tan alpha. So when theta equals alpha, r equals 0, means that the curve passes through the pole and has a gradient of tan alpha. The tangent must therefore be the line y equals x tan alpha, which is precisely the same thing as the line theta equals alpha. So we've proved the result we were trying to obtain. We now need to have a look at the area formed by a polar graph. So what we're going to suppose we're trying to do is find the area of the region formed by the curve r equals f of theta between the rays theta equals alpha and theta equals beta. And what we're going to do is we're going to take a small segment, a small sector, if you like, which approximates a part of the area that we've got to find. So this sector that we're going to take consists of the pole, so that's the origin, the point P with coordinates r theta, that's the polar coordinates r theta, and then a point P dash, which is a little bit further on the curve, with coordinates r plus delta r, theta plus delta theta. Now the area of that region can be approximated by the area of a sector with radius r and angle delta theta. And the area of that sector is a half r squared delta theta. We could obtain an approximation for the area of the whole region by adding up lots of these little approximating sectors. So we could say that the area is approximately the sum between theta equals alpha and theta equals beta of the areas of each of these little approximating sectors. So that's the sum between theta equals alpha and beta of a half r squared delta theta. The smaller the value of delta theta that we use, the more sectors we will have, and the more accurate the approximation will become. So we can say that the area will be the limit as delta theta tends to 0 of the sum between theta equals alpha and beta of the half r squared delta thetas. And we've seen in our previous work on integration that the limit of a sum like this can be written as the integral between alpha and beta of a half r squared d theta. Now, a lot of the questions involving areas of polar graphs are going to require us to integrate things like cos squared 5x or sine squared 7x. And you have seen how to do this in previous work, but you just need to remember that you have to use the identities that cos squared a is the same thing as a half of 1 plus cos 2a, and that sine squared a is the same thing as a half of 1 minus cos 2a. So for example, if I have to integrate sine squared 2x, I can say that sine squared 2x is 1 half of 1 minus cos of 2 lots of 2x, in other words 1 half of 1 minus cos 4x. And once I've done that, the integration then is relatively straightforward. So let's move on to our next example. We've got the diagram shows the polar graph of r equals 3 plus 2 cos theta. We've got to find the region enclosed by the curve. So we know that the area is given by the integral of a half r squared d theta with appropriate limits. In this case, we're trying to find the area inside the whole curve, so we need the limits to go from 0 right round to 2 pi. It wouldn't matter if you use minus pi round to pi, you'd end up with the same answer. But 0 to 2 pi just keeps everything nice and positive. So we've got to find the integral between 0 and 2 pi of a half of 3 plus 2 cos theta all squared. So multiplying out the brackets, that's the integral between 0 and 2 pi of 9 over 2 plus 6 cos theta plus 2 cos squared theta. Remember that we can write cos squared a is the same thing as a half of 1 plus cos 2a. So we've now got the integral of 9 over 2 plus 6 cos theta plus 2 lots of a half times 1 plus cos 2 theta, or the integral between 0 and 2 pi of 11 over 2 plus 6 cos theta plus cos 2 theta. And this integral we can now write down. So we've got 11 over 2 theta plus 6 sine theta plus a half sine 2 theta. We need the value of that when theta equals 2 pi minus the value of that when theta equals 0. So we've got 11 over 2 times 2 pi, which is 11 pi, plus 6 times sine of 2 pi is 0, plus a half of sine of 4 pi, which is also 0, minus, when we put 0 in, all we get is 0 plus 0 plus 0. So in other words, we're ending up with this curve that we've been looking at having an area of 11 pi. Now for our final example, we're going to be asked to sketch the polar graph of r equals e to the 0.2 theta for values of theta between 0 and 2 pi, and find the area of the region whose boundaries are this curve and the rays theta equals 0 and theta equals pi by 4. Drawing this graph actually is quite easy because we know that when theta equals 0, r is 1, and that as theta increases, r is increasing exponentially. So we've simply got a graph where the value of r is increasing as we go round the clock face, if you like. So as theta increases, r increases. And what we're after then is calculating the area of the region between theta equals 0, which is the initial line, and theta equals pi by 4. So the area we're trying to calculate is that shaded area there. We know that the area is going to be the integral of a half r squared d theta. So in this case, we've got the integral between 0 and pi by 4 of a half times e to the 0.2 theta squared d theta, which now e to the 0.2 theta squared is just e to the 0.4 theta. So we've got the integral between 0 and pi by 4 of a half e to the 0.4 theta. Doing the integration, that's going to be 1 over 0.8 times by e to the 0.4 theta. So I have to calculate the value of that when theta equals pi by 4 and subtract the value of that when theta equals 0. So I've got 5 over 4 e to the 0.1 pi. Take away 5 over 4 times by e to the nothing, which is just 1. So the exact value is 5 over 4 times e to the 0.1 pi, take away 1, or the approximate value is 0.461. And that concludes our look at the use of calculus for polar curves.